General Relativity, Lecture 1. For relativity, central is the notion of mass. There are actually two kinds of mass. The inertial mass, which appears in this Newton's law, so we put an index I there, and the gravitational mass, which appears in the gravity law. We have two masses there, and we put an index G there. There's no reason why those two masses actually should be the same. Nevertheless, there is an assumption of proportionality that the inertial mass is proportional to the gravitational mass. We can illustrate that with a pendulum. So here is a pendulum with a gravitational force, and here is the equation of motion for the pendulum. And I put in the two masses explicitly, mi and mg. We solve the equation of motion, and we arrive that the second derivative of the angle equals the ratio of masses times g over L times sinus L. The question is this ratio equal to 1 universally, to k universally, or is it characteristic of a material? This brings us to the weak equivalence principle, which answers that question, and it says that inertial mass is proportional to the gravity mass, universally, always. If you think about this, this leads to a consequence. The consequence is all three bodies in gravitational field move with the same acceleration. This is known from Galileo times, at least it's attributed to the Galileo. So we formulate the Galileo principle that a free motion in gravitational field is only determined by the initial velocity of the body and by the gravitational field. In particular, is that does not depend on the mass of this body. General relativity pushes the idea even further by saying that the inertial mass and gravitational mass are the same quantity. A consequence of that is that if we have a cap which freely falls in the gravitational field, this is equivalent to an inertial reference frame. It also means that the inertial force is equivalent to gravitational force. And this brings us to general relativity. We can formulate the Einstein equivalence principle. And that can be easily illustrated with an elevator cab. It's a special elevator cab. It's made of bricks, and they're put together without mortar. So they hold together only because they move with the same velocity, not because they would be glued together. It's small enough. That's important because the gravity across this cab is always everywhere homogeneous. And it's observed only for a short period of time, so the gravitational field does not change during that short period of time. This illustrates what is called the local inertial frame. Let us now formulate the Einstein's equivalence principle. It says that all local inertial frames are equivalent. We can apply this to this illustration of the elevator cabs. And so this would be like saying that all the elevator cabs are equivalent. All processes which happen in them happen in the same way. Let us make some comments on this. The first one, the free falling elevator cabs are actually also equivalent to elevator cabs which would hover somewhere in a far distant universe so that no gravity acts on them. They are all equivalent, the free falling and the hovering cabs in the rest. The second comment is that the equivalence principle is not only valid for mechanical processes, it's valid for all processes that are described within the local inertial frames, not only mechanical. That's important. The third comment is that the processes must be enclosed within those elevator cabs. So, for example, if you look at process like Bremsstrahlung, which would escape from this elevator cap, then the equivalence principle does not apply from that because Bremsstrahlung goes out of the elevator cap. We will introduce coordinates. In local inertial frames, the coordinates which we introduce are normal. We call them Minkowski coordinates because there's time and there are spatial coordinates. Now globally in the whole space-time, we introduce some set of global coordinates which actually connect the different local inertial frames. Now the general relativity theory is a prescription about the transformation between the global coordinates and the different sets of the local inertial frames and the local coordinates there. What about motion? In local inertial frames, all bodies move on straight lines with constant velocities provided that no forces act on them. Globally, this is not like that. The bodies move as straight as possible in a curved space-time. What does that mean? Or this is called motion along geodetics. Now, what are geodetics? They are the shortest connection between 2 points in a curved space or space-time. Let us illustrate what geodetics is. Suppose you want to fly from Prague to New York. So let's draw a globe with the meridians and with our small Europe appearing here, and there will be Prague somewhere there, and on the other side of the ocean there's North America, and somewhere there's Long Island and there's New York. When you fly the shortest distance, but when you look at the globe, well, it's not straight line at all, it's actually curved, but it's the shortest distance on the globe. So this is geodetics. And with the help of geodetics, we actually reformulate the Galilei principle by saying that bodies with the same initial position and velocity move along the same geodetics. Let us now look at the gravitational redshift, and we first derive this in an intuitive way, which is not really correct. It will be with the help of quantum mechanics and using the photon. You can think about why it's not really correct. The energy of the photon is h times the frequency, and we'll introduce the mass equivalent of this energy according to the Einstein relation. This is energy divided by the square of the light velocity. Then the increase of photon energy when it moves in the gravitational field is given by the difference of the gravitational potential. So we can write that dE, it's the increase of the energy, is minus this mass equivalence, time d phi. d phi is the change in the gravitational potential actually. Then we put in for dE, this is h times d nu, this equals the right hand side, and if we work this out, then we arrive at the right hand side, h divided by c squared times nu times d phi. So from this we can derive that d nu equals divided by nu equals d phi divided by c squared with a minus sign. Now this equation can be integrated, and we end up with an equation for the ratio of two frequencies for the photon at the different places with different values of the gravitational potential. Now we can get rid of the logarithm and write the equation just for the ratio of the frequencies. So frequency at the place b divided by frequency at the place I is given by this right hand side, which means that if at the place B the potential is higher than at place A, then at the place B the frequency of the photon or the frequency of the light will be lower. Next we derive the gravitational redshift kinematically. Imagine we have an elevator shaft, which will be the representation of the local inertial frame, and this cap is falling in a shaft, so this is a free fall. There is our shaft. Now there is a photon entering this shaft, this cap from above under the angle theta. The size of this cap is L, and the photon for an observer in the local inertial frame, so an observer in the cap, the light reaches the floor in the time which is given by L divided by c times cosine theta. Let's now look at the situation from the point of view of the observer which is outside of the cabin. The cap is originally at rest and it started accelerating with an acceleration g. So in the end of the acceleration, this observer moves against the cap so relatively to the cap with an opposite velocity. The velocity is minus v. This also means that he moves sort of against the light with the relative velocity which is equal to v times cosine theta. Now because of this, he observes a Doppler shift of the light frequency. And the Doppler shift, the shift of the frequency, is given by this relation, which is then GL divided by c squared, which is minus the difference of the potential divided by c squared. And we obtain the same equation for the redshift. Let us now talk about the speed at which a clock would operate at different gravitational potentials. To summarize the argument before working it out, because it's complicated, let me say that the clock which is at lower gravitational potential ticks slower, and the clock which is at higher gravitational potential ticks faster. So lower goes with slower, higher goes with faster. Now let's go to the argument. And to illustrate that, let's draw a situation with two clocks, A in place A, at the gravitational potential phi A, and B, the clock at the gravitational potential phi B. Now, they can sort of synchronize. They're identical atomic clocks, so the processes going on at both of them are completely identical. They tick with exactly the same internal frequency because there's equal processes. But phi B is higher than phi A. So now what can happen is that the clock A sends light to the clock B. And let's say the crest of the light wave, they will be the ticks. So you can count the crests, and by counting the crests you count the ticks as the clock A ticks. Now we have derived how the frequency of the light changes with the gravitational potential. So once the light from A arrives at B, the frequency nu B will be changed. It's nu A times this factor e to minus 1 over c squared, and then phi B minus phi A. I mean, the phi B minus phi A is positive, so we arrive at lower frequency than was phi A. That means that to clock B, the clock A appears as ticking at lower frequency, as ticking slower. And that is because it really ticks slower at the lower gravitational potential. Let's work out this argument with the help of a Gedanken experiment. We will use two clocks and we will put them in place B. Clock 1 and clock 2, there is a gravitational potential phi B. We'll move one of the clocks to the place A with a lower gravitational potential, and it'll stay there for a long time, so that the time is much longer than the travel time. The clock 1 always sends light to the place B, and the clock 2 always emits the same light. Those two clocks are identical, and we will count the crests from clock 1 and clock 2. So here's the situation. It's place B, place A, we put two clocks at place B. Clock 1, clock 2, they're identical atomic clock. Now we'll take the clock 1 and move it towards A. It always, all the time, sends the light, so we count the crests at the place B. Remember, the green light arrives with a red shift, so there are less crests. Now we move the clock 1 all the way to A. All the time it sends the light to the place B, the light arrives there. We count the crests, there are less green crests because the frequency 1 is smaller than frequency 2. It's red shifted. So it seems like the clock 1 ticks slower. It indeed does tick slower because it's at lower gravitational potential. Less crests, slower ticking. The clock 1 goes slower. Now the clock 1 will be taken and it returns to the place B, and we can now all together count all the crests arriving from clock 1 and clock 2. There will be less crests arriving from clock 1. So clock 1 has lived shorter time. I mean, there has been less crests. The time has been running slower for clock 1. That's the correct way to put it. So the clock 1 delivered less ticks. It was running slower, and it was running slower because it was sitting at lower gravitational potential. So it really shows that the time goes slower at the place with lower gravitational potential. It should be said that this effect is actually measurable. It has been measured by atomic clock, by a pair of atomic clocks which were placed, one in Greenwich, which is roughly 30 meters above the sea level, another one in Colorado, which was roughly 1650 meters above the sea level. And the difference between those two atomic clocks was about 5 microseconds per year. This is also a relevant effect if you're synchronizing the GPS satellites and using the GPS for tracking. As the next application, we're going to consider the bending of light in gravitational field. So let's consider a light wave, and the light wave enters the gravitational field. We put a local inertial frame where it enters the gravitational field. So it's like putting an elevator cab there. Now, in this local inertial frame falls freely with the acceleration g, and light propagates on a straight line in that local inertial frame. So that means that the trajectory of the light outside of that local inertial frame, outside of the elevator cap, will be curved. We introduce coordinates in the local inertial frame which will be unprimed, and prime coordinates are global. This is the sketch. The light goes straight, and in local inertial frame, this is the description of the motion. X grows with time like this, Y grows with time like ct sinus theta. Outside of the local inertial frame, X is the same, and Y, which is vertical, is changed, and there is this second term, 1/2 g t squared. Now we can express time with the help of x. So time is expressed like x over c times cos theta, which is the same as x prime over c times cos theta, and then explain y prime with the help of this x. So then y goes like c t sinus theta minus 1/2 g theta squared. Now we use the upper relation for time and obtain this form, 1/2 g x prime squared c squared cos theta squared, and this can be manipulated further, and we obtain the equation for y squared, which is then quadratic in x prime squared, like this. This is our final expression. Now we want to calculate the curvature of this trajectory, and so before that we need to know what the curvature is. Now we define the curvature, and we do that with the help of a circle. Let's draw a circle just in a while. Okay, so here are the axes, y and x. This is the center of the circle with its coordinates, and well, this is a circle by definition. Okay, and it has a radius r. Now the curvature will be defined as, actually there is a mistake, there should be minus 1 over r. Now the equation for the circle is the following: x minus x0 squared plus y minus y0 squared is equals r squared. We want to get to r, but first we want an equation for the y. So here's the equation for the y, and now we will be using the derivatives to get to the curvature. So first we take the derivatives of this curve. Now this is easy because everybody can take derivatives. dy by dx, you can calculate this for yourself, and this is the result: x minus x0 over r squared minus x0 squared under the square root, and we'll denote this by a, and then the second derivative can be calculated, and it has two terms. The first one is 1 over, minus 1 over square root r squared minus x0 squared. Then there is x minus x0 squared, and then the same denominator in the power 3 halves, and we denote this b. Now if we evaluate this for x equal x0, then it's easy because a vanishes and b can be evaluated, and it's minus 1 over r. And so this is minus the, well, actually there should be plus the curvature because the minus sign is wrong. I'm sorry for that. Yeah. And so we can obtain the curvature from the derivatives. Now, generally, let's obtain this 1 over r or minus 1 over r from a and b. That means from the first and second derivative. And to that end, let's rewrite b this way. So write b like this, and we can manipulate this again with the help of a. So the second term in the brackets is actually a squared. Again, recall what we want to get. We want to get 1 over r, or actually minus 1 over r, because minus 1 over r would be the curvature. So let's get to that. Let's write this. This is from the equation for b. We want to express this x minus x0 under the square root, so we will help ourselves with the first derivative. Now from the first derivative, we see that the x minus x0 squared is equal to a squared times bracket r squared minus x0 squared. It's again there, so we manipulate this equation, and from this we can actually express x minus x0 squared as r squared a squared over 1 plus a squared. You see, we replace with this the term under the square root over there. So let's use it. Let's put this equation down here so we see what we're manipulating. And now the blue circle will be put under the square root. Here it goes, the square root is here. And also we put the minus sign on the right hand side to the b. So now it's manipulation of this equation, and we can express r. Actually, that's what we wanted. R equals to something. We still can rewrite the left hand side, and then we arrive at the simplest expression for the right hand side. Now kappa equals minus 1 over r. This is the correct with the minus sign. Curvature is minus 1 over r, and this is the formula. B, I recall, b is the second derivative and a is the first derivative. Now let's get back to the light trajectory. We had this trajectory, we had its second derivative, and we had its first derivative. This was the trajectory, y prime equals x prime tangent theta minus 1/2 g over c squared cosine squared x prime squared. Now let's evaluate the first and the second derivative at x prime equal to 0. Okay, so this is the first derivative, this is the second derivative. We still keep the x prime there, but then when we put x prime equal to 0, the b is there now. This is our expression which we want to evaluate, and let's insert for a and for b. So this will be minus g over c squared cosine squared divided by this bracket 1 plus tangent squared theta to the power of 3/2. This is evaluated already at x prime equals to 0, and now this can be manipulated when we rewrite the tangent squared a little bit. So that's what is happening here in the bracket, and when the cosines in different powers get cancelled, we get to the final result, which is minus g cosine theta over c squared. And this is our result for the curvature of the light trajectory. That kappa equals g cosine theta over c squared.